What's up, guys? Welcome back to the 12 ISLs of Christmas. Today we are back with 2018 IMO shortlist problem A1, which is a nice functional equation from the 2018 shortlist. So the problem is shown on screen. We want to determine all functions f from the positive rational numbers to itself, satisfying the relation shown on screen for all x and y in the positive rational numbers. So how can we get started on this problem? Well, one thing to try is to make two of these terms equal, because we only have terms that are wrapped in f. So if we make two of those equal, then we can make one of these equal to 1, and therefore we get an x such that f of x equals 1. But which two terms should we set equal? Well, we can't really set this equal to anything because there's a squared term there. So let's try setting this equal to this. And the best way to do this is by letting x squared f of y squared is equal to y. Because then obviously if you input each side into f, you'll get the same thing. So the best way we can make this possible is if we let y equals 1, because then we want x squared equals y over f of y squared, so that y is a perfect square of a rational number. So plugging y equals 1 makes this work out. So we get x squared equals 1 over f of 1. So x equals squared there, and x equals 1 over f of 1. So we would like this to happen. So let's see what happens when we plug this in. So if we plug in x equals 1 over f of 1 and y equals 1 into the given equation, the first term just becomes 1 over f of 1 squared, because that's x squared, times f of 1 squared, because f of y equals f of 1. So that's just f of 1 squared, just f of 1. Then we get f of 1 over f of 1 squared, and then f of 1. Then we can cancel these guys out, because we know they're not 0. So f of 1 over f of 1 squared is equal to 1. And since it is positive, we have f of 1 over f of 1 is equal to 1. Now this will be very useful to us. Okay, so now we know that f of 1 over f of 1 is equal to 1. So what can we do now? Well, let's look at this expression again. We have f of y squared and f of y, but we don't directly involve y in this equation. Whereas we involve x in this equation because we have x squared, we only care about the value of f of y, not what y is itself. So let's try making f of y equals 1, because then that simplifies both sides greatly. And we can do this by letting y equals 1 over f of 1. Because then we get that f of y equals 1, and when we plug this in, we get f of x squared times 1 squared, so that's just x squared, is f of x squared times 1, so that's just f of x squared. And we get this miraculous identity shown here. And indeed, since x squared equals x only when x equals 1, we can plug in x equals 1 here to get f of 1 equals f of 1 squared. And that implies that f of 1 is equal to 1. Okay, so now we know that f of x squared is f of x all squared. And as a corollary, f of 1 equals 1. Notice how I had f of 1 over f of 1 is equal to 1 from earlier, but f of 1 equals 1 just conquers this. Because f of 1 equals 1, just plug it into here and you get the same thing. So this piece of information is dealt by f of 1 equals 1. Alright, so now let's see how to apply this to the original problem statement. So immediately we have a perfect square inside the left-hand side. So let's go ahead and bring that outside with this identity shown here. And when we do that, we get f of x f of y squared is equal to f of x squared f of y. And now let's see what we can do with this. Since we have f of x squared on over here and an x term over here, we can just let x equals 1 because that will simplify it a lot. And in the end, we get f of y is equal to f of y squared. This is a really interesting identity because, for one, we have a squared term over here, which means that f of y is equal to a square for all rational numbers y. But then that means that this side here, f of y, is also a perfect square. So this term here is a fourth power, which means that f of y is a fourth power. I think you can see what is going on here, because that means that this is also a fourth power, which means that it's an eighth power, which means that f of y is an eighth power. And we can just keep doing this. In general, we get f of y equals a 2 to the nth power for all positive integers n. Now this should definitely sound very fishy to you. Any rational number is not an arbitrarily large power of some other rational number. For example, if we consider 16, then this is a fourth power because it is 2 squared. No, 2 to the fourth, my bad. But it is not an eighth power because it is square root 2 to the power of 8, and this is not a rational number. So we can't continue this forever. And the only way we can have this happen is if f of y equals 1. Because then 1 is always 2 to the nth power, because 1 to the power of 2 to the n is 1. But this doesn't work for any other rational number for clear reasons. And this means that f of y equals 1 for all rational numbers y. And we can check that the solution works by plugging into this equation here. We get 1 equals 1 squared times 1, and that is indeed true. So what's the takeaway from this problem? Well, we just plugged some random stuff in, stuff that we would hope would work out, and in the end, we ended up getting important identities such as this. And given the form of the problem statement, we applied this lemma here to it, and we got this. And since we wanted to make it a bit simpler, we just got rid of one of the leading terms and turned it into this. And using this, from here, we remembered that f goes from the rational numbers to the rational numbers, the positive rational numbers to itself. And that means that we can just repeatedly use properties of it. In particular, we use that f of y is a square, and also a fourth power, and an eighth power, and a 16th power, and so on and so forth. In general, it is that 2nth power of some other rational number. And clearly this is nonsense for the rational numbers, unless it is equal to 1. And that gives us our solution. So the moral of the story is to just play around with certain values that you think would work out, use the domain to your advantage, and use it to derive a contradiction in some sort of way, unless we have f of y's of a certain form. So thank you so much for watching this video, and I'll see you tomorrow for the next one.